This video explains how to generate code from AADL model to C or XML and generate code for ARINC653 operating systems. The model we are using is the ARINC model. We have a web page that explains all the model detail and how to reproduce this demo. You can find more information on aadl.info/aadl/demo-ARINC653/. On this page, you have links to all the tools required to do that, and also an overview of the model and how to generate code. And we also have video, and you can expand the video and everything. The video we are doing today, it's more complete and will go through all the details about how to generate specifically for two operating systems, VxWorks and DIOS. The ARINC model was presented in the AADL committee and was designed by Jérôme Hug and his students at Israel, France. This presentation is available on the AADL wiki, and you can have all the specific detail about the modeling patterns and how they implement the model. Presentation of the model is beyond the presentation, this video. If you want to find the slides, you can find them on the AADL wiki. This model is available on the OpenAADL GitHub repository at this address, github.com/openaadl/aadllib. This is an Eclipse project. You can find the ARINC model in the example directory under the directory ARINC. You can import it and then use it in Usate. Once you import the project, you see the project in your Usate environment. There is different AADL file. The main model is in model.aadl. When you open it, the textual AADL editor will be shown. We can look at the graphical representation of the model. We click on the open diagram and it will show the implementation of the model with all the different subcomponents. Basically, the AADL model consists of four main processes. The first one we have is the PR that runs the actuator. The 6 actuators that are in fact captured and specified with 6, one for each actuator. If we trace that down, we see that these actuators are connected from the health monitoring, the shared health monitoring, and the main process. We see that we have 4 partitions that are captured with an AADL process. Each partition has several AADL threads that are ARINC653 tasks. To capture the memory isolation, we bind every partition to a different memory segment. This is shown in AADL with the association to a memory segment. At the bottom left, we see the memory, and the memory is divided with 4 different memory segments. And we have one memory segment for each partition. Same thing for the processor. The processor model, the physical processor, but also the partition runtimes. Basically, the different runtime to execute every partition that separates in terms of time the different partition. Every partition is bound to a memory, space isolation, as we can see here with the arrow. And the partition is also isolated in time and associated to a virtual processor. This is a graphical view. Let's have a look at the textual specification and the AADL properties. In the main model, we have the system implementation, and we create a variation for each operating system, one for DIOS and one for VxWorks. Let's have a look at one of them. For example, the DIOS. If we look at the DIOS, we see that we extend the regular implementation and we add some property for the DIOS code configuration. But let's have a look at the processor, so in the EMPL. So, for example, the CPU over there, we see that the processor component contain different virtual processor, one for each partition. And here we see and look at the properties, and we see that for each partition, we have a slot for each partition of 1 millisecond. So we define the time isolation policy in the processor component and describe how much time do we allocate for each virtual processor, basically each partition. But to generate code, we need to define the isolation policy in the processor. Also, we need to define this isolation policy in the memory, what we call the space isolation. So we have a look at the memory, the main memory component. If we open up this memory, we see that the main memory has 4 subcomponents, memory subcomponents, and every memory subcomponent has a base address and a memory size. It will define how much size we allocate for the partitions. So we associate the process, that are the partition, with the memory and processors using the property actual processor binding. So we say that the first virtual processor is associated with the ACPR, ACCPR partition, the memory segment. ACC mem is associated with the ACCPR process, and so on. Once we have the model, we can generate the code. As we say, there is 2 code to generate. The configuration code for the kernel and the code for each partition, which will be C code. To generate code for each operating system, we select on the outline the system implementation, that is the root system. We click on it, click on the Ocarina Bridge, and then select the type of code we want to generate. For example, let's generate the configuration code for DIOS, right? Select it, and we see in the console, we have some outputs from Ocarina. Let's have a look. In generated code, I have a configuration file called diosconf.xml. So I can open it with a text editor, for example, and then it shows the XML configuration for my kernel. So it says that I have several partitions, partition 1, partition 2, and so on. It explains the duration. If you remember, the duration is 1 millisecond. So basically here we say that it will be 1 millisecond, and we scale this value to the value that DIOS expect. We also explain a detail and specify all the different ports, sampling port and queuing port for the partition. If a port is a source, a destination, and what is the size of the data that is specified in the AADL model. So we use all the information from the AADL model to generate this. So by generating the code, we make sure that both the model and the code are consistent. So we have the third partition and the fourth partition, and we generate all the different time frame, the different time slots for the partition, and the health monitoring policy. All right, so we did that for the DIOS. What about VxWorks? If I select my VxWorks model that has just some properties specific to VxWorks, and I generate the configuration file. Okay, I see that, okay, my generated code already exists. And then open the file for VxWorks. I open it in the text editor, and I see that the code, the structure of the code XML file is different. But in fact, I report exactly the same information. In this file, I see an application, and I see the different ports of my application. I also see that I have a duration, and you see here that the unit is different. So we scale the ADL property to the unit the tool you are working with expects. So you don't have to care about the implementation detail. Everything is in the model. You don't have to know exactly the detail about VxWorks or DIOS. You work at the model level. So you work at a higher level of abstraction and don't have to care about all implementation aspects. And it has been verified at the model level. So you don't need to make any verification in the implementation code. And it connects the different ports, so the port between the different partitions. So it also makes all the configuration of the channel, the communication channel. So we generate also the health monitoring policy, and finally also all the memory allocated to each partition. Okay, so this is the kernel configuration. Let's have a look pretty quickly to the code for each partition. So it's exactly the same thing to generate the code for the partition. We select the root model. So here, let's do that for VxWorks, and we have the same for DIOS. And we click on the Ocarina bridge, and then we select generate VxWorks code. Okay. Generate code, and then I refresh here, and I see that I have a bunch of code. In the generated code, main CPU contains a directory, and it contains a directory for the kernel that is here empty. I mean, there is just file, but this is just called skeleton. The 4 directories that we are really interested in are ACC underscore HM, ACC underscore PR, ADIRUP underscore PR, and shm_pr. This is the code for each partition. So if you remember, we have 4 partitions, and for each partition, we generate the code to create the task, create the port, sampling port or queuing port, and connect them with a subprogram and the task. Let's have a look. If I open the C code, it's actually pretty neat because in Eclipse we have also a C editor, so I can have syntax highlighting. In the code I generate for each partition, it's really a code for ARINC653. So we create all the resources first, the tasks, the communication channel, and so on. And then we start the task that are basically periodic tasks or sporadic tasks that wait for an event. So in the main.c file, I create all the resources for the partition. So for example, create a sampling port, create the queuing ports, and then create every task. So here I have one task to create, and then I start the partition. This is the main.c. So create the resource, communication channel task, and start the partition. So here we have an entry point that is ACCHM job. So this task, in fact, this entry point is all the subprogram that are executed by the task. So let's have a look at the code generated here. So in fact, it will realize what the partition is doing. So we generate also a bunch of external statements for the communication channel identifier, generate all the value, and implement the task. And here the task is reading sampling message, receive a message from a queuing port, call a subprogram, and send. So the code pattern is the following: receive the message, process the value that are received, and then send what the subprogram produce. So receive, process, produce. And the subprogram ultimately call a C subprogram, but you can also call subprograms that are implemented in Scale or Simulink. You can generate C code from Scale or Simulink, and you can call that code. Ultimately, if you want to see the subprogram that is called, you can see that in the subprogram.c code. And we eventually call this subprogram that is provided by the user. Something really interesting is here you don't have to know all the specifics about ARINC653. If you look at the code that is generated, it includes all the file, all the compilation units required by VxWorks or DIOS. So you don't have to write any code. You don't have to know the specific about the development platform. Everything is already provided and generated by the code generator. And the code generator takes care of all the small variation between ARINC653 implementation. If you have an ARINC operating system and you want to migrate to another one, they will always have some minor difference, and you have to handle that and modify your code. The code generator takes care of it. So if your model is validated, when you call the code generator will make sure that all your model will have the same execution semantics between both implementation with the first operating system and the second one. As we mentioned, we have also a code generator for DIOS. So if you have a look here in the main.c file, we include Apex and different file, Apex sampling and queuing. If we generate the code for DIOS, we might see some minor difference in the code, meaning that the code generator will in fact adapt the generated code for DIOS, and it will take care of some implementation details. If we look here, we don't have so much file included. We only have apex.h included. This is how DIOS handle the management of the ARINC API. In fact, the code generator takes care of all these minor differences, and you don't have to worry about it. To integrate the code in VxWorks, we need to create a project for each partition and integrate the generated code, the C code, for each partition in each project. So we have one project for the first partition P, one for SHM, one for ACC, and one for ACCHM. After that, we have also a project in VxWorks for the partition OS, the runtime in each partition. So every partition is using this project that represents the runtime for the partitions. We use the default values. And then the configuration for the OS that will configure the kernel, the VxWorks kernel that will use the XML file. And we have a project for the configuration. And here in this project, we import, in fact, the XML file generated by Osate and Ocarina. So we have exactly the same file that is integrated in the VxWorks environment. And finally, we have a project called ADIRU that integrates all the project together to make the final system. So in the configuration project, I import my configuration file generated by Ocarina and Osate. And in all the partition projects, we had all the generated code. And you can see, for example, in main.c, that all the resources are created correctly. Once the code is generated and compiled and the system is built, we can run the actual system. So we can run it on a device like your board, either your execution board or a simulator. So in VxWorks, we can do that with a simulator. So in that case, we have here a target, and we launch it inside the VxWorks development, and we connect on it. So we can see the result. It launched the VxWorks OS. So we see the output on the simulator, and then we see some output from the application, which is not so exciting. But basically, this is what the system do. Actually, when you deploy the real system, it will execute the code on the platform and send data to the actuator and so on. But in the simulator, we cannot see that. We can also import the code in DIOS. In DIOS, we'll have to create at least one project for each partition. So if you remember, we have 4 partitions. We have also to create a project for the configuration and one for the simulator. So we have one project, SHM, P, ACCHM, and ACC for each partition. And in the configuration project, we have the file we generated with OSAT and Ocarina. So if we look at this file, we're gonna have all the information we have in the AADL model, is all the information with the different resources, the partition, the size, and so on. In the partition, we'll have the source code, that we see previously and that is generated by Ocarina and OSAT. And the simulator just configure DIOS to run the project. So as for VxWorks, we can use DIOS to generate, to compile the project and integrate it and run it on the target. In other words, the hardware you want to use for your project. We can also use a simulator. So this is what we are doing right now. I will use the simulator, and we just have to start the target. So we select the target we already configure and launch the simulator. So once the simulator is up, we synchronize all the files that have been built from the AADL model and the generated code, and we upload that into the target. And then it runs the accelerometer and starts the system. And we see some errors that are reported by the application code. So it just output a lot of string and text from the application code, which is not really exciting because in the real world it should send data on the actuator, but basically it shows you that the integration is correctly done.